Hi everyone. In this chapter, we will explain stereochemistry of organic compounds. You can refer to chapter 4 in John McMurray book for additional reference material. Also, what you need for this chapter, we've talked about this at the beginning of the semester. What you need is a molecular model kit. So if you did not get this by now, then we can go around with it. It's fine. And I'll show you how to build your own molecular model using simply Play-Doh and matches. This is kind of like an inexpensive way. Having molecular models with you when you are solving the problems is really very important. You can buy these molecular models on Amazon, but since we started the chapter, if you don't have them by now, it's fine. Just don't buy them because it's gonna be too late when they arrive. So let's start by explaining the term stereochemistry. Stereochemistry basically is the study of the three-dimensional structure of the molecule. You are basically studying the orientation of the molecule in space. This is what stereochemistry is. So we can simply observe the stereochemistry of the molecule by simply considering starch and cellulose. Both starch and cellulose, they do have the same repeating unit. The difference here is that in cellulose, see, the repeating unit is the same. However, in cellulose, the oxygen joins two rings using two equatorial bonds. On the other hand, for the starch, the oxygen atom joins the two rings using the equatorial and the axial bonds. So due to these differences in stereochemistry, basically starch can be digested in our body but not cellulose. So far we discussed isomers, and we said that isomers are one type of isomers is constitutional isomers. This is the only isomer that we've discussed so far, is constitutional isomers. In this chapter, we're going to cover the rest. We're going to cover the rest of the types of the isomers. So just a quick revision on constitutional isomers. Constitutional isomers, these are isomers that have the same molecular formula, but they have different connectivity of atoms. This means that constitutional isomers, they have different IUPAC names, they do have different physical properties, they do have different chemical properties, but their molecular formulas are the same. Now, with respect to stereoisomers, now stereoisomers is basically it differs in the way that the atoms are oriented in space. So basically, you're studying the orientation of the molecule in space, the rotation. When we say orientation, we mean the rotation of the molecule in space. They still have the same molecular formula. So constitutional isomers and stereoisomers, they have the same molecular formula, and this is the definition of isomers. They have the same molecular formula, but either you can write them differently. This means that the connectivity of the atoms is different, or you can rotate the molecule, and by rotation you end up getting a different compound. You end up getting a different compound with different properties, but it's still having the same molecular formula in there. So the connectivity for stereoisomers are the same. So you still have the same molecular formula, same connectivity of atoms in there, but the difference is the rotation in space. So they differ in configuration. Configuration is basically the three-dimensional arrangement, which is the rotation of the molecule in space. And we will talk about the configuration of the molecule in here in a second. So this is the difference between constitutional isomers and the stereoisomers. So stereo, the moment we say stereo, we mean by that rotation. So you are doing a rotation of the molecule in space. So it's either the rotation or the orientation in there. 2-methylpentane, 3-methylpentane, these two have the same molecular formula but different connectivity of atoms. So this is why they are called constitutional isomers. On the other hand, for stereoisomers, stereoisomers have different, basically it's different types. And one of the types of stereoisomers is the cis and the trans. The cis and the trans, they do have the same molecular formula, but the basically the rotation of the molecule in space differs. Okay, the connectivity or the orientation, the orientation of the molecule in space is different. Here, the two substituents are on the same side, so this is why we call them cis. Here, the two substituents are on opposite sides, we call them trans. You guys just remember one thing in chapter 4, that in a chain there is basically no cis and trans. When we are working with alkane chain, no cis and trans. Why? Because there is basically a free rotation around the carbon, single bond carbon. So you can do a free rotation in there, so there is no cis and trans. On the other hand, in the cycle there is no free rotation. It's basically locked. So this means that whenever I have the substituents on the ring, I need to specify these substituents, what they are with respect to each other. Are they on the same side or are they on opposite sides? Because if I write 1,2-dimethylcyclopentane, this is not a complete name. I have to specify what's the orientation of these two substituents with respect to each other. Again, are they on the same side or are they on opposite sides? Let's have an example. Classify each of the following compounds as constitutional isomers, stereoisomers, or not isomers. So constitutional isomers, they should have the same molecular formula, different connectivity of atoms. Here you go. Different connectivity of atoms, same molecular formula. This is constitutional isomer. This is an example of another constitutional isomer. This is an example of another constitutional isomer. Same molecular formula, count your carbons, hydrogens in there. They are exactly the same, but the connectivity of the atoms are different. So this means that every time you write the structure, you end up getting a different name. So this is going to be constitutional isomers. Now for the stereoisomers, it's the orientation of the molecule in space. It has to do with rotation. So here I am having two substituents on the ring. In this structure they are trans, in this structure they are cis. So different orientation of substituents. This is stereoisomer. Same thing over here. This is a trans, and then I have a chair conformation. Look at these CH3s. This CH3 is axial. This is up. This is equatorial. This is up. So these two CH3s are cis with respect to each other. Both are on the same side, which is up. Cis trans. Immediately, this is a stereoisomer. This is trans. Oh no, you know what? This is basically an OH over here. See, this is an OH over here. This is a hydrogen in there. These are different molecules. These are not even constitutional isomers, because if you take a look at the molecular formula, each one of those is going to have its own molecular formula. They have different molecular formulas. So this is why they are not isomers. Everything has a mirror image. And a mirror image may or may not be superimposable. Now, what do I mean by superimposable? I mean align with each other. Some molecules are like hands. So if you take a look at your right hand and your left hand in there, the right hand and the left hands are mirror images of each other. So if you put your left hand in front of the mirror, you're gonna see its image. Its image is gonna be the right hand. So if you take the left hand and put it on top of the right hand, you can see that your hands, they don't align with each other. This is the term which we say basically the molecule and its image are not superimposable. So by definition, a molecule or an object. So here I'm having an object, but we will go back to organic molecules in a second. So a molecule or an object that has its mirror image not superimposable on it is said to be chiral. So we are going to explain the first term over here, chiral. Chiral is basically a molecule where its mirror image is non-superimposable on it, does not align with it. So this is called a chiral molecule. On the other hand, other molecules here are like, for example, like socks. Chair is also another kind of object that is achiral. So if you put one pair of sock in front of the mirror, you're gonna see its image. If you take that sock and you align it with its mirror image, you see that they align. This means that they are superimposable. So we're gonna say that the object is gonna be achiral. So by definition, a molecule or object that is superimposable on its mirror image is said to be achiral. So these are the two terms that we're going to use throughout this chapter, chiral and achiral. So now let's consider organic molecules in here. So we have water, okay? Water is made up of oxygen and two hydrogens. Let's put water in front of a mirror. We're going to see that water is going to have a mirror image. If you take the water and simply try to align it with its mirror image, it will align. The bonds will align. So if they align, then immediately we're going to say that water is achiral. Water has an sp3 hybridization. So you have two lone pairs over here, and its hybridization is an sp3 hybridization. So here I'm considering the case of an atom that is surrounded by two bonds. Okay, two bonds, four groups, two lone pairs and two bonds. Then in this case, the molecule is going to be achiral. On the other hand, if I have a molecule that is surrounded by three different groups, like for example here, CH2BrCl, this carbon is surrounded by three different groups. A hydrogen, so you have two hydrogens in here, this is one group. And then you have a bromine, and then you have, it's a bromine over here, and then you do have a chlorine over there. Let's go ahead and put it their mirror image. The mirror image basically will produce another molecule, but if you take this molecule here and you rotate, you're gonna see that their bonds are gonna align with each other. So just rotate the molecule. If you rotate the molecule and you're able to have the molecule aligning with its mirror image, then we're gonna say that the molecule is not chiral. Rotation can be in any direction. The rotation can be in any direction. So if you rotate in any direction, clockwise or counterclockwise, then and you can see that the molecule and the mirror image, they align with each other, then immediately the molecule will be achiral. Now if you can see over here, I can draw a plane of symmetry, and the plane of symmetry can pass through. I've oriented the molecule in this direction and here just to show you that I can simply draw a plane of symmetry. A plane of symmetry is an imaginary plane that normally you draw it throughout the structure, and it cuts the structure in half. One half is basically the mirror of the other half. And we can do this in this molecule over here. We can draw an imaginary plane of symmetry and cuts the molecule in half. If you have your molecular models with you, please go ahead and build these two sets in here and see that you can simply do a simple rotation and the bonds align. And if they do so, then the molecule is not going to be chiral. It's going to be achiral or non-chiral. These are the two terms normally that we use. Another way to check if the molecule is chiral or not is simply to draw a plane of symmetry. A plane of symmetry is an imaginary plane that cuts the molecule in half. If you are able to draw that plane of symmetry and end up having two parts of the molecule that are the same, then immediately the molecule is not chiral. See, I am able to draw basically a plane of symmetry through this oxygen here and cut the molecule in half. So this means that the molecule is not chiral. When you draw a plane of symmetry, the plane of symmetry, as we mentioned, is an imaginary plane, and that plane of symmetry since it's an imaginary plane, it passes through the object. It divides the object so that one half is the mirror image of the other half. The rule of thumb here is that when you want to draw the plane of symmetry, you can draw it anywhere you want. Anywhere you want. It really doesn't matter. It's just to choose a plane and to draw it along the plane. So see here in this structure, I'm just choosing a plane and drawing it along the bromine, carbon, and the chlorine. So I'm going to end up having two halves in here. That hydrogen and this hydrogen, these are basically mirrors of each other. So it's as if the plane of symmetry acts as its own mirror in there, producing two halves of the molecule. So this is why we can say that the molecule is not going to be chiral. Another type of symmetry that basically is a criteria for achiral compounds is the center of symmetry. The center of symmetry is basically a point that is situated so that identical components of the object are located on opposite sides, and they are at the same distance from the point along any axis passing through it. So this is called the center of symmetry. So if you are able within the structure to find a center of symmetry or to draw a plane of symmetry in there and cut the molecule in half, then the molecule is not going to be chiral. Now let's define chiral molecules. When is the molecule chiral? Normally the molecule is chiral whenever it has four different groups around it. Now notice here, I am basically limiting myself to a tetrahedral carbon, to an sp3 hybridized carbon in there. So a chiral molecule or a chiral center, okay? A chiral molecule in there is basically a molecule that has a chiral center, has one chiral center, and the chiral center is basically surrounded by four different groups. So that chiral center, I'm going to represent it as a small asterisk in here. This means that this is a chiral center. It has four different groups around it. Another name for that chiral center, it's called the stereocenter. It's called the stereogenic center. It's an asymmetric center. So you're going to see all of those names in your homework. Just know that we're talking about a center that has four different groups around it. So if I have a chiral center, if I have one chiral center, so we're going to talk about one chiral center now. If I have one chiral center in there, and I draw a mirror and look at the image of that center, of that carbon in there, I would see that that basically I'm going to end up having another molecule, B. Now, no matter how I do, no matter how I rotate A, so if you take A and you want to align its bonds with B, no matter how I rotate A, there is no way I can have the bonds of A aligning with the bonds of B. So this means that A and B are completely different compounds. They differ by rotation. The connectivity of the atoms is the same. Everything is the same, but the only difference is the rotation around the chiral center. So the point is, for the molecule to be basically chiral, it has to have a chiral center. A chiral center is a center that is surrounded by four different groups. So if you have a chiral center in there, and you want to draw the mirror image of your molecule, then your molecule is now gonna, your mirror image basically is not gonna align with the molecule. So the mirror image can never ever align with the molecule. So we say that the molecule and its image are non-superimposable, and we say that the compound is a chiral compound. So a chiral compound is a compound that has a chiral center and it has a mirror image. Okay? Now, we're going to give a name for A and B because A and B are completely different compounds. They are mirror images of each other. So A and B are called enantiomers. This is one type of stereoisomers. So what are enantiomers? Enantiomers are mirror images of each other. Enantiomers basically are chiral molecules. Because when I say chiral, I mean that they have a chiral center. And if there's a chiral center in there, if there's one chiral center, then definitely the molecule will have a mirror image. So the molecule and the mirror image are going to be completely different. So I would say that A and B are going to be enantiomers. These are stereoisomers. They differ in the orientation of the molecule in space. Specifically, they differ in the rotation around the chiral center. So the summary for chirality, for the molecule to be chiral, you need to have first a chiral center. So you should have a chiral center. So a chiral molecule must have one or more chiral center, stereogenic or chiral center in there. So if the molecule has one or more chiral center, then the molecule, there's a possibility for this molecule to have a mirror image. And if it does, then the molecule and the mirror image are going to be called enantiomers. This is going to be a chiral molecule. Normally, chiral molecules, they don't align with each other. So the molecule and the mirror image, they are non-superimposable. So as we said over here, everything has a mirror image. The question is whether the molecule and its mirror image are superimposable. If they are superimposable, then the molecule is not chiral. But if they are non-superimposable, then the molecule will be chiral and the molecule will have a mirror image. The molecule and the image will be called enantiomers. Any tetrahedral center with 4 different groups can be chiral. Here I'm giving not just carbon. Here I'm giving an example of nitrogen in there. Nitrogen can make 4 bonds. Nitrogen is an sp3 hybridization. So when we say tetrahedral, we mean sp3 hybridization in there. So nitrogen is an sp3 hybridization. So here in this case, 4 different groups, nitrogen is a chiral center. In general, a molecule that does not have a chiral center will not be chiral. This means that it's an achiral molecule in there. If we have one chiral center, then definitely the molecule is going to be chiral and it's going to have a mirror image. Now for this option here, we're going to clarify this as we proceed. If we have more than one chiral center, the molecule may or may not be chiral, meaning the molecule may have a mirror image or may not have a mirror image. Because when I say a chiral center is different than a chiral molecule. A chiral center basically is a center with 4 different groups. So just to clarify this, chiral center is a center with 4 different groups. A chiral molecule is a molecule that has a mirror image. So when I want to draw the mirror image of the molecule, simply, when I want to draw the mirror image of the molecule, let's say over here. So when I want to draw the mirror image of the molecule there, then whatever I see on this side is going to be on the other side here. It's going to be the first thing that I'm going to see. This is a CH2, this is a CH3 over there. Okay. You write it in a different way. So this is a CH2, that is a CH3, and then you have your phenyl group over there. You do have your hydrogen. See, I'm not changing anything. The CH3s are still in plane. Now my ethyl group is going to be behind. It's still behind. My benzene is in front. It's still in front, but I am just viewing the mirror image of it. So we were saying that a chiral center is a center that has 4 different groups around it. A chiral molecule is a molecule that has a mirror image. If you have one chiral center, then definitely the molecule is going to have a mirror image, so the molecule is going to be chiral. But if you have more than one chiral center, the molecule may or may not have a mirror image, so it may or may not be chiral. Now, to locate the stereogenic center or the chiral center, we said that a chiral center is a center that is surrounded by 4 different groups. So all what you need to do is just look at your 4 different groups. This is all what you need to do there. So your 4 different groups here are basically the bromine, the hydrogen, the propyl group, and then the ethyl group in there. See, these are the 4 different groups. So the moment you see 4 different groups in there, this means that this is going to be a chiral center. So simply we represent it by a small asterisk in there showing that it is a chiral center. Normally, chiral centers, they are sp3 hybridization. We're going to omit all carbons that cannot be tetrahedral stereogenic centers. We're going to omit the CH2s, the CH3s, because CH2, CH3s, they cannot have 4 different groups around them. They already have 2 hydrogens that are the same here and 3 hydrogens that are the same there. If we have any sp2 hybridized carbon, these are out of the picture. They are not stereogenic centers. They are not chiral centers. So we're going to limit our explanation in this chapter on basically chiral centers that are sp3 hybridization, and they are surrounded by 4 different groups. Let's have an example. So we have larger molecules. It doesn't matter what the molecule looks like, big, small. I mean, if you know the rule, a chiral center is a center that is surrounded by 4 different groups. So here, for this one, okay, I have, for this carbon, I have a group. Let me highlight this. So this is one group, this is the second, this is the third, and this is the fourth. Do you see it? All of that is the fourth. So this is a chiral center. The groups have to be different. This is a phenyl group, this is a CH2 phenyl, this is a benzyl group. A phenyl and the CH2 is called a benzyl. So these two are different. So this is why this is a chiral center. This is another chiral center over there. So that is another chiral center having also 4 different groups. Where's the group number 4? Group number 4 is basically the hydrogen here. Remember, every carbon has 4 groups around it. But here the 4 groups are different, so this is why I'm labeling it as a chiral center. So for this carbon over here, I do have a hydrogen, please don't forget. So here's my 4 different groups, 1, 2, 3, and 4. So 4 different groups in there. This is going to be a stereogenic center. I have 2 of them. Here, basically, yeah, these are the 2 different stereogenic centers there. Here I have 3 chiral centers or 3 stereogenic centers. So stereogenic centers are not limited to a number, so they can be 1, 2, 3, 4 up to infinity. It depends on basically the size of the organic molecule. As long as you can find out a carbon that is surrounded by 4 different groups, and please you guys don't forget that there's a hidden hydrogen in there in each one of them, okay? Because carbons always make 4 bonds. So if you see a carbon with a 3 bond, definitely the 4th one is going to be a hydrogen. Now, stereogenic or chiral centers on the ring. If you have a ring, of course, you can still have a chiral center as long as it satisfies the rule where the center needs to be surrounded by 4 different groups. 4 different groups in there. Now, take a look at methylcyclopentane. Methylcyclopentane has a hydrogen, has a CH3 on the carbon 1, and then it has a CH2 on this side, and another CH2 on the other side. See, these two are the same. So definitely carbon 1 is not a stereogenic or chiral center. If you want this to be a chiral center, all what you need to do is just make these 2 groups different. Here I have another example of 3-methylcyclohexene, but now I am making these 2 groups different over there, see? I'm making them different. So around this carbon, I have a double bond here, which is completely different than this group over there. Completely different. So I have 4 different groups around the center, carbon center. So this is why I'm gonna label this as a chiral center. So far, this molecule over here has 1 chiral center. Normally, all chiral centers, they are stereocenters. So this one over here for this carbon, this is a chiral center, and at the same time, it is a stereocenter. Why it is a stereocenter? Because I do have orientation of the groups around it. I do have the hydrogen behind, high OH in front in one, and then in another structure, I can simply swap them and make the OH to be behind and the hydrogen to be in front. So this is called a chiral center because it's connected to 4 different groups. It is a stereocenter because of the orientation of the atoms on that center in there. I can swap, so this is why I'm calling it a stereocenter. So all chiral centers normally are stereocenters, but the opposite is not true. Here I'm having an example of a stereocenter, a cis and a trans. This is a stereocenter where basically the CH3s are on opposite sides for the trans, and here the CH3s are on the same side for the cis. However, so these two are called stereocenters. However, they are not chiral. I don't have any sp3 hybridized carbon that is surrounded by 4 different groups. So this is not chiral center. So you don't have a chiral center in there, but you do have a stereocenter around the carbon double bond carbon in there. So now let's explain enantiomers and show you how to draw enantiomers. So as a summary, we said if you have a center that is surrounded, a carbon center that is surrounded by 4 different groups, then we say that this center is a chiral center. If it's a chiral center and it's 1 chiral center, then I can simply draw a mirror and draw the mirror image for it. Then the molecule and the mirror image will be enantiomers. They will be different. So the molecule and the mirror image, these two, are going to be different molecules because they have different rotation around the chiral center in space. So this is why they are different. So these enantiomers, let's label those enantiomer A and enantiomer B. Enantiomer A and enantiomer B, basically, so these two molecules are mirror images of each other, and they differ around the rotation of the chiral center in space. This is their difference, but see, the connectivity is the same. The connectivity of the atoms is still the same. Whatever is behind stays behind, whatever is in front stays in front. When you want to draw the mirror image, you guys, all what you need to do is just look at it in a form of a mirror. So whatever you see on this side, just go ahead and write it on the other side. You don't change the orientation of any of these groups around the chiral center. Whatever is behind stays behind, whatever is in front stays in front. So these two are enantiomers, meaning that they are mirror images of each other. These two are enantiomers, they are mirror images of each other. See, I am seeing a bromine in front on this side. When I want to draw the mirror image, the first thing that I want to see on the other side of the mirror is this CH3, this carbon over here. Then I would see the CH2, then I would see the CH, and then I would see the bromine. See, the bromine is still in front, the hydrogen is still behind, and then the rest of the molecule. So the molecule and the mirror image, they are non-superimposable. These are enantiomers. No matter how you rotate A, there is no way that A will align with B. If the bonds of A align with bonds of B, then this means that A and B are not mirror images of each other. They are the same. If the bonds align, then the molecule is going to end up being the same. There is no way that they are enantiomers of each other. This is another example, drawing enantiomers in a form of a cycle. So again, you need to locate the chiral center. So in order to draw a mirror image, you need to have at least one chiral center. So if you have a chiral center, then it doesn't mean that the molecule is chiral. If you have a chiral center in there, draw its mirror image and see. If you have one chiral center, then definitely you have a mirror image for it. But if you have more than one chiral center, there's a possibility that you don't have a mirror image. We'll talk about this. So let's have an example in there. Draw in a plane of symmetry for each of the molecules. As we mentioned, the plane of symmetry is an imaginary plane that cuts the molecule in half. So we have a propyl group over there. If we draw an imaginary plane passing through the middle carbon, then it's going to cut the molecule in half. So this is going to be your plane of symmetry. For the cis 1,2-dimethyl cyclopropane, then again I can draw a plane of symmetry basically through this carbon here. It cuts the molecule in half. I can do the same thing over here. If I have an ethyl cyclobutane, then I can draw a plane of symmetry through the ethyl group. So it's going to be through the ethyl group over here. If I have the CH3 and the cyclobutane, these are on the these are basically aligned. Okay, the CH3 and the cyclobutane, if I have them in plane, so these two are going to be in plane. They're having the hydrogen in front and the other hydrogen is behind. I can simply draw a plane of symmetry. Now for this one, it will really help if you draw the molecular model for it. So if you have just any carbon in here, and then if you draw a simple plane of symmetry, if you make the molecular model and you draw a simple plane of symmetry through, you're going to see that these two hydrogens over here, they basically going to be mirrors of each other. So basically your plane of symmetry cuts the molecule in half. It's better viewed when you draw the molecular model for it. In D, I can simply draw a plane of symmetry between the two carbons, between these two carbons in there, and since the chlorines are on the same side, I'm cutting the molecule in half. So see, all of those, they are achiral molecules because I can draw a plane of symmetry cutting the molecule in half. Draw the mirror image. The moment I say mirror image, this means that I have at least one chiral center. So if the molecule has a mirror image, this means that the molecule is going to be chiral. Let's have an example. So draw the mirror image of each molecule, label the molecule as chiral or achiral. So you look at the stereogenic center in here. So this is going to be our chiral center. This is going to be our chiral center in there. So you represent the chiral center by a small asterisk. Okay, well, first look, see, I have two CH3s in here. No, this is not a chiral center at all. So this carbon over here is not a chiral center because I don't have 4 groups around this carbon. I have 3 groups because these CH3s are the same. So this means that if I attempt to draw a mirror image of this structure and then do a rotation and try to align the bonds, they will align. They will align. So the bonds are going to align. So the molecules are going to be identical. See, those two are identical. They are not mirror images of each other. So we're going to say that the molecule is an achiral molecule. And see, I can simply rotate this and draw a plane of symmetry. And the plane of symmetry basically through these two CH3s, it cuts the molecule. So I can, I can draw a plane of symmetry through the chlorine and the bromine and cuts the molecule here in half so that the CH3s are going to be mirrors of each other. So now my plane of symmetry can basically be around the chlorine and the bromine. So that is going to be my plane of symmetry in here. So let's say if I extend this a little bit and if I extend this a little bit and draw a simple plane of symmetry, and that plane of symmetry passes through the bromine and the carbon and the chlorine. So it's going to cut the molecule in half, and I'm going to have the CH3s on both sides that are going to appear as mirrors with respect to each other. So I'm going to say that the molecule is achiral. Here I have a chiral center. I have 4 different groups around the chiral center. So this is going to be my chiral center in there. 4 different groups around the chiral center. So immediately my molecule is going to be chiral. So I have a chiral center. My molecule will have a mirror image. No matter how I align A, no matter how I rotate A, there is no way that A will align with B. So I would say that A and B are called enantiomers. They are mirror images of each other, and the molecule is chiral. So when we say a chiral molecule is a molecule basically that has a mirror image. Diethyl ether, I can simply draw a plane of symmetry through this oxygen here. It cuts the molecule in half. So if I am able to do this, then I'm going to end up having identical structures. So the molecule and its image are the same. So I cannot draw a mirror image in this case. So I would say that the molecule is achiral. And it is because I don't have a chiral center with 4 different groups around it. This is a chiral center, 4 different groups, so I can easily draw a mirror, draw an image for the molecule in there. No matter how you rotate this molecule, there is no way that its bonds will align with its mirror image. So we say that the molecule and the mirror image, they are enantiomers. They are a pair of enantiomers, and the molecule is called a chiral molecule. These are basically some biological active molecules in there, just to show you that molecules can be big and the number of chiral centers can be more than 2 or 3. So it depends on how big your organic structure is, and apply the definition that a chiral center is a center with 4 different groups. So this is going to be 1, 2, 3, and of course don't forget the hydrogen. Every carbon is a tetrahedral, so if there are 2 bonds in a plane, one is behind, the other is going to be in front. So this hydrogen is going to be in front. This hydrogen here is going to be behind. Let's write it outside. This hydrogen here is going to be behind. This hydrogen here is going to be in front. This hydrogen here is going to be in front, and so forth. So the idea for a chiral center is a center with 4 different groups.